Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC2006. Now for today's lecture 8, we're going to do something different. Since I've given you the tutorial questions before the break last week. So I thought that, for today's lecture, we are going to discuss on the answers to the questions that I gave. And this is also to ensure that you understand how to do the exercise, and at least you understand how to actually apply the equations or the concept that we have covered so far. Okay, so there are not many questions, but the questions do actually zoom on the part that make use of the, as I said, the equations that you need to use and how to apply it, and also some of the things that we've talked about, how do you actually apply that concept. Okay, so the first question is, what is the resonance frequency of fluorine nucleus in a magnetic field of 14.1 Tesla? So once you see the word resonance frequency, immediately you know that you have to use the Lama frequency. So it's just another name for Lama frequency. Lama. So then if I make this bigger, we can see on the screen. Okay, so the Lama frequency, here's the equation. So it's you have the gyromagnetic ratio, and you also have the you just point. So the gyromagnetic ratio, and you have the magnetic field, and over 2 pi. So all you have to do is look at the table that's given in the notes at the end of the tutorial here. And so the magnetic field is given as 14.1. So you get the resonant frequency to be of this value. Okay, so that's it. So make sure that you remember this is one of the important equations that you need to remember. So this is how you actually apply that, and this is how the questions based on resonance frequency or Lama frequency will be asked. Okay, and question 2 is based on the subtlety that I mentioned to you in class, perhaps in the first lecture. So what will be the magnetic field strength on the NMR spectrometer in question 1? What do I mean by the magnetic strength label? So you have the NMR machine, right? So you have the NMR machine. So what is the label here? Okay, is it 400 megahertz, or is it 300 megahertz, or how many megahertz? So this is the label. This is what the question is about. What is the label? So how do you know what is the label here? Well, remember I told you that the label of the spectrometer is based on the proton nucleus. Okay, so then all you have to do is just find the Lama frequency for proton. And so you're using the same equation but addressing it on proton, because that's what the label is based on. So you find the gyromagnetic ratio, which is given here, and times again with the magnetic field. So you get 600.34. Well, that's close to 600 megahertz. So what you'll see here, the label will be 600 megahertz, right? Okay, now the next question. Arrange the following molecules according to the highest chemical shift to the lowest chemical shift. Now from this, this is the part when we talk about what contributes to the values of the chemical shift. And from this, you know that the electronegativity is one of them based on the patterns that you see here. And so you know that the electronegativity increases as we go up, group 7, okay, as we go up to this, okay, so it increases. So you see that the chlorine has a very high electronegativity compared to bromine and iodine. And so electronegativity increases as we go up, hence it will be more deshielded, okay. And so for chloroform, you can expect that the 3 fluorines that is going to reduce the electron density, and so you have it's going to be much more deshielded as compared to the others, okay. And so this is the arrangement of the what you call the chemical shift from the highest to the lowest, okay. Of course, you know, you don't have to so the what you call the periodic table is given, so I'm just showing it here again so that you can see. All right, true or false, the Zeeman splitting for proton in 400 megahertz, true or false, I'm looking at this question, okay. The Zeeman splitting for proton in a 400 megahertz NMR spectrometer is smaller than that of this phosphorus. 31. State your reasoning. Now, when you talk about Zeeman splitting, okay, so immediately you have to think about what is the energy of the splitting. So the energy of the splitting is equals to this. Now, then you have to think, all right? So this H bar is a constant, doesn't matter which nucleus you're looking at. The magnetic field is also constant. So what is different is the gyromagnetic ratio. And so based on the table, and I already told you before that proton has the highest value of gyromagnetic ratio. So each nucleus will have its own value for gyromagnetic ratio. And so proton has the largest, and if it has the largest, so the Zeeman splitting for proton should be bigger, okay. So then this means that this statement is false, okay. So this is just to remind you again, the question number 5 is on the what you know, what can you get from a proton NMR, you know, this the information that you can get, and this one specifically talk about the integration and the splitting pattern. So the integration talks about the relative areas under the signals, okay. So that means you have here like this, and some will have fixed like this, and so you'll see something like this for the integration, okay. That's finding integration. So, and what does it say? It means that how many hydrogens of each type, okay. So you know that there will be more of these hydrogens of this type of proton as compared to this one. And the splitting patterns means that, so if you have something like you know, you have a doublet here, and then you have something, or it should be much nearer, and you have something 1 2 1. So it says something about, so this is 1 to 1 and this is 1 to 1, so it says something about the neighboring. Okay, so question number 6, why is carbon 12 NMR inactive while carbon 13 is NMR active? Okay, why is that? So clearly, as we have seen before, it's due to the spin number, okay, because the spin number for carbon 12 is 0 and it's non-zero, or 1 for or half for carbon 13. So it means that, you know, you can see once you have a value for this spin number, so it is going to be NMR active. Now, describe how the line width of an NMR spectrum is measured. Now, if you remember that you have, this is really a bad drawing, but you get a point. So if this is, let me draw that again. So if you have something like this, okay, say this is the baseline. So this is the height. So roughly at half height is here. So then this is half the height, okay, half height. So that means this is where the line width of the peak is. That's where you get the value for the line width. Okay. Now next, since we talk about this splitting patterns, okay, sketch the proton NMR spectrum for an AX spin system. Okay, how will that look like for this AX spin system? Okay, remember? So this is when you need to look back at the lecture notes. In case you find that, oh, how did, you know, Dr. Isaac get that, you know? So that means that you need to go back to the respective lecture notes so that you can understand why. So you dig up. It's all in the lecture notes that we've covered. Okay, so the AX system, and it says here spin A is more deshielded, so it should be, oh my god, my drawing. So I'm not good at sketching, especially with when it's on the screen. So when you have an AX system, so you know that A is more deshielded, so it's going to be, you know, at the upper field here. Okay, so it's neighboring with X. Okay, so that's only, and you only have one species. So you have the n+1 rule. So that means you have a doublet because it's neighboring with X. Remember, this splitting is based on what the neighbor is, okay? And then you have this is just a sketch. Okay, so you don't know exactly the chemical shift. So again, X will be feeling the environment of the A system, which also has one species, so it's also a doublet here. So doublet. So for an A2X3 system, okay, so A again is deshielded, okay, so it's feeling the environment of the X, and X has 3 species, so n+1, that's 4. And remember that based on the Pascal triangle, so you have 4 is going to be 1, 3, 3, 1 intensity. So you have, and make sure when you sketch that it looks like 1, 3, 3, 1. So that's almost, again, this is just a sketch, and so it should, you know, as long as, but even if it's a sketch, at least it shows that intensity. And because the X3 sees that of the A2, and that has 2 proton there, okay, so we're saying that this is a proton NMR, right? So it's a proton NMR. So then it will be n plus 1, so that 2 plus 1 will be 3. So remember, based on the Pascal triangle pattern, it's 1, 2, 1. So you'll see that you need to see 1, 2, 1. So again, the intensity, it doesn't matter, with respect to this, but as long as you see that the intensity is 1 to 1, about, okay? So you get the idea, all right? So that's how you should answer this. Please do not answer this individually by saying, okay, you do AX system, you separate that as in like this, because it should be in one spectrum. So it should be this and this, okay? All right, so I think that's the last question for that part, and this is my favorite part. Okay, when was the last time you did a crossword puzzle? So maybe you don't do that. It's not the trend now, but this is quite nostalgic for me as a kid. So I thought I want to bring back this in the form of tutorial questions in the form of crossword puzzle. So I do hope that you attempt to answer, okay? So let's do it. Okay, again, my writing is going to be really scribble, but I hope you understand. So he developed the first one across, that's that, okay? That's this part. So he developed the high resolution of this NMR technique and won a Nobel Prize. So I think we have a few names there. If you look at the Nobel Prize, what do you call the Nobel Prize winners that I've shared with you. But because you're not so sure which one, so we keep it. We leave that one first, okay? Because that doesn't look so obvious. So let's do the number 4. What's number 4? Number 4, across. The scale of the chemical shift is expressed in what? And it's an abbreviation. Well, we know that. So it's going to be ppm, right? The chemical shift will be in ppm. So, all right, then we scale up, okay? This word, so this word is not included in MRI due to its negative connotation. Well, we know the answer to that. It's going to be, what is it? Nuclear. People are scared of the word nuclear, so you don't want to have that in the MRI. So the next clue, NMR works by applying the electromagnetic by applying this electromagnetic wave frequency. That's radio frequency, right? So we have here radio. Okay, I'm only going to give you for today's lecture only this video. There's no slides or anything. Okay, I'm only going to give that. So the next clue is when the energy from the EM wave frequency is enough to flip the nuclei when the energy of the EM wave is enough to flip the nuclei from its lower energy level to higher energy. So it has to be at resonance, right? So that's resonance. I hope you had fun doing this, and I really hope that you actually do it. Okay, it is the most common nucleus studied in NMR. That has to be proton. Okay, then the type of magnet used in NMR spectrometers. Okay, so what can it be? The type of magnet used, it has to be superconducting. That looks long, so that must be correct. Superconducting. Okay. Next, the key to ace this class. Okay. Well, what does it say? That's not 16. Well, it can be anything. I'll tell you that in a bit. Okay, this gives information on the molecular environment of the hydrogen atoms in a molecule. When you talk about molecular environment, information on that, and there are two words, so there must be a space. Definitely that's the chemical shift. Chemical. We have a blank here. Shift. Okay, and let's go here. The number of liquid state NMR department has. Well, what can you actually fit here? I can only think of THREE. We have 3. Okay, the energy splitting between alpha and beta spin state is proportional to the Zeeman splitting. Okay, so proportional to its 2 words. And it's a long one, I think. So it has to be gyromagnetic ratio. That looks right. So gyromagnetic. Then blank ratio. Okay, that looks fun. Okay, then biologists study these macromolecules using powerful NMR spectrometer. So these, biologists and macromolecules, I can only think of which one is it? So 4 down. Protein. PEI. Is that protein? There must be an S, right? So there must be an S because macromolecules. So proteins. Okay, this is macromolecules. Then you say this. Okay, so it must be plural. Organic chemists use NMR to elucidate what structures? There has to be molecular structures, of course. So molecular structures. Okay, and occurs when the energy levels of the spin states are equal. So when there's no magnetic field, so it's the energy is equal, and then only after that you have that Zeeman splitting. So that state is called, again you can see that it starts with D there, it has to be degenerate. Right. Okay, next occurs when the number of hydrogen environment acetonitrile has. So acetonitrile is CH3, and then we have the triple bond, right? Acetonitrile, is that right? So you only have one environment of that. So so number 9 down. So it's only one type. So it says that O here. How convenient is that? So it has to be 1. Then we have the NMR tube is inserted in this spectrometer. Okay, the NMR tube is inserted in this spectrometer, so it's inserted in a probe and then inside. Okay, so number 10, let's stand down. There you go. That's PROBE. Okay, and one of the liquid gases used in NMR, it's either helium or nitrogen. So 13, well, you can only fill it as helium here based on this. Okay, alright, so we're good so far. This is added to the sample in the NMR tube as a reference. So of course that has to be TMS. Alright, which one is it? Where is it? Yes. So we have TMS. And the mathematical tool used to obtain an NMR spectrum. Mathematical tool. It has to be Fourier transform. So FD, since it's abbreviation. And finally, the time-based NMR signal. Well, not finally, we still have one more. 2 more. The time-based NMR signal abbreviation. What is it? FID. Okay, and if you're transform, then you get the frequency base. So FID is the time base. Okay, which one have we not answered? The first one. He developed the high resolution NMR. So if you look at the names, I can only think of one that ends with the letter T. So who do you think that is? If you look at all the Nobel Prize winners, so that must be Ernst, E-R-N-S-T. Okay, all right, so this could be anything. All right, what is the key to ACE 2000 SIC2006? Okay, what is the key to ACE 206? What's the key to ACE this class? So what's the answer for number 16 here? What do you think? Well, let me tell you. The only way to the only way to ace this class, the key to ace this class, starts with the letter D, ends with the letter N. Can you guess? I'll give you 5 seconds. What do you think? Well, if you answer this, you should pat yourself. Daddy. Okay. This is indeed the key to ACE. Not only this class, this course, but all the courses they're taking. So there you go. That's the solution to the tutorial. And on the screen now is the answer to my scribble answer to the crossword puzzle. So I hope that I do hope that you actually did the exercise, the tutorial. And so if you can't answer the questions, I do hope that you look at the lecture notes that pertain to the exercise and start doing your revision. Okay, so I hope you enjoy, especially this crossword puzzle. Okay, I'll see you in the next lecture right after your break. Okay, all right, so that's it for now. Thank you, and Assalamualaikum warahmatullahi wabarakatuh, and stay safe and take care. Bye for now.